Here's another application of using elementary row operations to find various things about a matrix. Here we are trying to find the rank of the matrix A over here and find a basis for the column space, find a basis for the row space, and find a basis for the solution space AX is equal to 0. The solution space of this homogeneous equation is called the null of this matrix A. Okay. We use the same matrix so we can save time to get the row echelon form. We already know what to do. So this is going to be R1 added to R2 and negative 2 R1 and added to R3. Alright, and then this is what we have. We have 1, 4, 2, and then this is 0, 12, and 4, and 0, negative 9, and negative 3. Okay, and then we say rescale. This time let's make to the really row echelon forms, the leading one, and 4 and 2, and then this is 0, and this is 1, and this is 1/3, and then of course this is 0, 0, 0. We are skipping several steps over here. Let me just say dot, dot, dot. Over here we have several steps, and this is now the row echelon form. We say leading one over here, leading one over here, and we have this form over here like that. Okay, so now we know that the rank is simply equal to the number of leading ones, and so that is going to be simply equal to 2. Rank of this matrix is equal to 2. Now a basis for the column space. We know the column space over here. The column space is the span of these three vectors of v1, v2, and v3. Okay. And we see that the third vector over here is dependent on the previous one. So this is really equal to the span of v1 and v2, since v3 is dependent on v1 and v2. We know we can cast this v3 away without changing the span. And v1 and v2, these vectors, the corresponding vectors over here, these two vectors over here, these are v1 and v2. Okay, v1 and v2, v2 and v3. Okay, and these are w1, w2, and w3. And then we have these two columns over here are linearly independent because they have leading ones over here. So the corresponding vectors over here, they are linearly independent. So what we have over here is that the span of these three vectors, 1, negative 1, 2, and 4, 8, negative 1, and 2, 2, 1, is simply equal to the span of these two independent vectors, linearly independent vectors. Okay, so we can say basis for the column space. We simply use these two. Basis of the column space is simply two vectors, v1 and v2. Okay. Now, we cannot really use w1 and w2 because w1, w2, they are basis of the span of w1, w2, w3. And even though the relations, the linear dependence between these vectors, they are not changed, but these spans can be different because of the row operations. Okay, so we have to go back to these two vectors to find the basis for this span. Now how about the null of ax equal to 0? We can still go from over here. Okay, this is the same thing. The null of A matrix 1, 4, 2, negative 1, 8, 2, 2, negative 1, 1 is the same. As that of this matrix over here, 1, 4, 2, 0, 1, 1/3, and 0, 0, 0. That's what we started with. We say they have the same solution set. Now let's go back to the way that we solve for the solution set, because we want to find the space over here. So we can say, oh, this is x plus 4y and plus 2z is equal to 0. Remember, it's homogeneous, so we are not really putting these 0, 0, 0s over here. And this is going to be y and plus z over 3 is equal to 0. And z over here is the free variable because we don't have a leading one for this column. So now we have over here y is equal to z over 3 and x is equal to negative 4y and minus 2z. So we have, now we put it inside, negative 4z over 3 and minus 2z. Okay, I think I lost the negative sign over here. Y should be negative z over 3. And then this is going to be positive. Okay, and then this one over here we should have over here negative 2 over 3 and z. Okay. So that's what we have. And then in the vector form we have the following. Look at, we have x, y, and z. Remember, z is the free variable, so we simply have z over here, right? And then y is negative z over 3. And x is negative 2 over 3z. So if we pull out its common factor, z over here, then this is what we have, 1 over here, and z. Remember, z is a free variable, so we can actually change it to s or t like this. So we have negative 2, 3, negative 1/3, and 1. And this is the solution set. S is arbitrary. S is arbitrary over here. What it means is that the solution space is simply this vector space. This span, you can say, the span of just one vector. This vector over here, we have negative 2/3, negative 1/3, and 1. Okay, and that's the span. And so the basis for the null or the solution space is simply one vector. We can say it's just one vector. And if, since vector you can actually rescale, you can simply put down negative 2, negative 1, and 3 multiplied by 3 over here. And that is the basis for the solution space. And so we know the nullity over here, nullity, the dimension of this space is the number of vectors in this basis is simply 1. And of course we have verified that the rank plus the nullity no, I think just nullity over here. Alright, let me erase this part over here. Okay. Nullity is the nullity is 1. So, and we have nullity is equal to the number of columns. Number of columns. And that's equal to 3. 2 plus 1 is equal to 3. Now, if we want to find a basis for the row space, what we need to do over here, let me just indicate how to do it. You just need to look at A transpose, because now A transpose, in A transpose, rows become columns. So what you have over here is that if you want to look at first row, now it's over here, second row is over here, and third row is 2, -1, and 1. And then you perform the row elementary operations over here, and then we can actually get the same kind of basis. The basis should consist of only 2 vectors over there.